my colleague from StatPhys Kolkata to take over.
Thank you, Anando. Hello, welcome again to the third session of StatPhys Kolkata. In this session, we are having 6 talks from eminent speaker and also one graduate student on focusing on dynamics of glassy systems, collective behavior of active particles, pattern formation, etc. We have in this session, we have 3 talks of 25 plus 5 minutes duration, and there are 3 short talks of 12 plus 3 minutes duration. And our first speaker is Professor Ronald Dickman. Ronald is a professor in the physics department of the Universidade Federal de Minas Gerais in Brazil. He works on statistical physics, stochastic processes, and also on neuroscience. So today, Professor Dickman is going to talk about phase diagram and interfacial instabilities in a driven lattice gas model. So Ronald, over to you.
Thanks very much. Let me try to share my screen and get my presentation up. Screen.
See, if I remind you after 12 minutes, will it be okay?
Sure.
Okay.
I have a timer, but please remind me because I tend to get lost. So that's no problem. Okay, let's see. Now I have to go to my presentation. Okay, presenting. Let's go to full screen and see if this all works. Okay, can you see my presentation?
Yes, yeah, yes, perfect.
Okay, so, sorry. Again, thanks very much for allowing me to present. And at very short notice, I only found out about this meeting a couple of weeks ago, and I was eager to present something and see many old friends and people that I know by name. It's about 9 a.m. here, almost 9 a.m. here in Brazil, but I understand it's late afternoon where you are. So this is my talk. I'm going to talk about a driven lattice gas model that has 2 species that repel each other, which is based on the Whittam-Rawlinson model. These are my colleagues and a couple of references where you can find out more. So, of course, I'll explain what the model is, talk about phase separation, principally under the drive, where it's more interesting and a new topic, define an order parameter and phase transitions, and look at some other details, and then briefly describe some attempts to derive a kind of field theory for this model and mention some open questions. So to begin, the Whittam-Rawlinson model is an important model in equilibrium phase separation because it's one of the models where you can actually demonstrate rigorously phase separation below, or I should say above, a certain critical density. So the original model is in continuous space, and there are 2 particle species, A and B, that between A's or between B's, there's no interaction whatsoever, but AB pairs interact via hard sphere excluded volume interactions. And as you might expect, when the density becomes high enough, these 2 species have to segregate spatially. So that's what happens. And it's interesting to observe that all of the ordering, actually everything that happens in this model in equilibrium, is due to entropy maximization. The lattice gas model in equilibrium is a variant of this in which 2 particles of any species can't occupy the same site. And in addition, there's nearest neighbor exclusion between A and B particles. So now there's an Ising-like phase transition to coexisting phases above a certain critical density. And what I'm going to talk about now is when we apply a bias to the hopping probabilities of these models. The bias is the same for both species, and it's represented by this parameter P, which is an asymmetry parameter for drives in the positive horizontal and opposite direction. So you see maximum drive happens when P is equal to 1, then it's simply impossible to hop contrary to the drive. So what happens? These are typical ordered configurations. Without a drive, you see this kind of amorphous phase separation into A and B rich phases. But under a drive, something surprising happens, which is that there are stripes, A and B rich stripes, that form perpendicular to the drive direction. This wasn't what I was expecting because my intuition was based on the attractive lattice gas model, Kotzlevovitz-Spohn model, in which a stripe forms along the direction of the drive. But we can see that such an arrangement, in fact, would be unstable in this case. Now, let me show you a video. So I have to exit this presentation and get to my video. This was done by a former master's student of Max Leventovich, and he was kind enough to give me permission to show this film. So let me run it. Now the film starts out with the particles segregated into a single stripe, but are you seeing the film? I should ask. Can you see the video?
Yes, we can. Yes, yeah.
Okay, great. So that original configuration of a single stripe is unstable for these parameters, and you'll slowly see it break up and form a series of stripes, a series of vertical stripes that become better ordered, although we'll also see a defect dynamics. Now let me stop this for one moment to point out that you see a kind of static, and that's the vacancies. We've gone into more or less the frame of the pattern. It's not perfect. So you see the stripes moving along, but there's a very high velocity movement of the vacancies in the direction opposite the drive. The drive is to the right, but since we're almost in the co-moving frame with the stripes, you see these vacancies zooming along to the left. Then you see minority species like these two B's, let's say, in a sea of A's. And of course, they have to be accompanied by chaperones that separate them from the majority. So these move rather slowly. In fact, in the laboratory frame, so to speak, they're frozen until a boundary comes along to pick them up. So let me run this a bit more. Sorry. Oh, there it goes. Okay. So now you can see more or less the stripe wavelength, the preferred wavelength forming, and you see a dynamics of defects. It's quite curious. Eventually, you can get perfect stripes, but probably we didn't have enough time in this video to see that. Another observation is that the shape fluctuations are highly correlated between neighboring stripes. So fine, I think this gives you a pretty good idea of what goes on. And let me go back to the presentation. Right. Full screen. Okay. So a number of surprises depending on your point of view. I was certainly surprised to see its stripe orientation perpendicular to the drive. The trees are rough, which is also different. to the case of attractive interactions. And there's a preferred wavelength. And you can get quite well-ordered patterns if you add the particles slowly as the pattern is forming. Interfaces along the drive, as I'm showing here, are unstable. They develop large fluctuations and then reconnect through the periodic boundaries. So, okay, a bit about characterizing the configuration. The important point is to define a column-wise density and AB difference. And actually the AB difference, which I will call psi, is what's important in defining an order parameter associated with the stripes. So we take a Fourier transform, a discrete Fourier transform of this quantity, and then we look at the Fourier mode with the highest amplitude, and that defines our order parameter. You can see that here, a Fourier series. M is the number of stripes, and for example, for this set of parameters, there's a clear preferred wavelength, or preferred wave vector, which translates to a wavelength. Here is the behavior of the preferred wavelength as a function of density for several different drive strengths. Now there appears to be a phase transition. Here I'm doing a kind of finite size scaling analysis and looking at the envelope. You have to remember that even though there's a preferred wavelength, not every system size is really coherent with that wavelength. So as you vary the system size, there will be certain sizes that work well for that wavelength. An integer number of wavelengths fits well in the system size. And then there are sudden drops. So we have to look at the envelope of this signal to judge if we're at a phase transition or in the subcritical regime and so on. So these are more recent data tending to show that there's a critical value, a critical density around 0.765. Okay, I'll skip that because I'm running out of time. And let's look very quickly at the disordered phase below the critical density. There are a couple of surprising features. One is a pair of maxima in the wave vector components along the drive. So in other words, even in the disordered phase, there's a preferred wavelength to correlations along the drive. The correlations decay spatially with an exponentially decaying envelope, but it's a decaying oscillation, so there is a preferred wavelength. Okay, that tells me that my time is up, so I'll finish very quickly. Regarding the theory, Max and Royce and myself as a minor contributor have developed a kind of field theory description using Doi-Politi type of formalism. And what they've been able to show, most interestingly up to the present moment, is that the two fields, the charge, the species difference, which we call charge, and the overall density, the total density, have different velocities of propagation. And this appears to lead to this preferred wavelength, at least in the disordered phase. How that connects with the stripe preferred wavelength is yet to be seen. So, okay, these are some conclusions and some open questions. Do we really have long-range order? That you might ask, because we're looking at a two-dimensional system with modulation along a single direction, something like a symmetric, and that in equilibrium would be unstable. but perhaps the drive stabilizes this. So that's what I'm able to tell you in this short period. This was supposed to have lettering that says thank you for your attention, so I'll just say that and try to answer any questions that you may have.
Thank you. Thank you, Ronald, for this very beautiful talk. And now the session is open for question. Yes, so I could see there are raised hand from, yeah, SS Manna. Yeah, Professor Manna, please go ahead. Hello?
Hello?
Yes. Yeah, Professor Manna.
My microphone is okay.
Okay. Yeah.
So my question is that how the things depends on the strength of the drive, in the sense that suppose I make the drive P tends to 0 plus. So there will be a segregation, but I would expect some patches rather than the stripes. Is this okay?
Yes, it's hard to study that limit explicitly, but what I can say is that the stripes get wider and wider as the drive weakens. Formally, in the limit of drive going to 0, the wavelength should tend to infinity, right? You should just have these amorphous domains of A and B's. So yes.
So how the average stripe width depends on the strength of the drive, that is known, or have you already told us that?
How does I didn't understand which quantity?
With the width of the stripe.
Yeah. They tend to get smaller as you reduce the drive. I'm sorry, they tend to get larger. The lambda tends to get larger.
As P tends to 0, it becomes larger.
Yes.
So
yes.
Some inversely proportional to P or something like that.
Yeah, I wouldn't go that far, but that's inversely proportional.
Okay.
But it does diverge as P tends to 0.
Okay. Thanks.
Okay, we will take another quick question. I could see that PK has raised hand. So if there are some quick questions, then we can. PK, please go ahead. Do you have a question?
So I was asking that, you know, for the finite size scaling, determining the envelope is very hard. So how exactly, because there will be a lot of errors in calculation of the envelope.
Let me see if I can go back to that image very quickly. Okay, so here are, let's say, the raw data, and we're looking at the maximum. I mean, we expect that as you sweep the system size, there are going to be roughly periodic in L sizes that support because they're coherent with an integer number or close to an integer number of wavelengths for that particular density and drive. So after a while, you learn where to look, and when you do that, now you can. These are only the maximum. These are the most favorable cases. For example, at this density, I've gotten a preliminary idea first, and then I know where to look, and so that's how I can do a finite size scaling. Of course, not every L, even if it's close to an integer multiple of the preferred wavelength, they're not all equally good because they're not exactly, the preferred wavelength is not an integer number.
Okay, thank you.
Yeah. Okay, so let's thank Ronald again and move to the next talk.
Thank you very much for your attention. Let me stop
thank you. Yeah, thank you. Yeah, so our next speaker is Professor Sharika Mohitrovatacharya. Sharika is a professor in Polymer Science and Engineering Division and National Chemical Laboratory in India. She works on dynamical properties in liquids and soft matter systems, including polymer physics and complex fluids. Today, Professor Bhattacharya is going to talk about heterogeneous dynamics of supercooled liquid. Sharika, over to you.
Yes, am I audible?
Yes.
Yeah. So thank you, Ruby, for the kind introduction, and thanks to the organizers for organizing this conference and giving me an opportunity to speak here. Now, since there's not much time, I'm going to quickly start the talk. So what I'm going to tell you now is why supercooled liquids have heterogeneous dynamics. Now, before I go over to the talk, acknowledgement, this part of the work, initial part of the work was done in collaboration with Professor Chandan Dasgupta, Dr. Manoj Kumar Nandi, and former student of mine, and Mohit Sharma did this work. Sorry. I've lost the presentation.
Yeah, okay. That's true.
Yeah. It's just that I wanted to hide something and it just I lost it. Can you see it now?
No, not yet.
So
I think you have
just
to.
give me a minute. And
Not a problem.
so yeah. So now and the funding, of course, from DST and CSIR. Now, quickly, what is dynamic heterogeneity and why do we care about it? Unlike normal liquids, where the liquid dynamics is supposed to be homogeneous, in supercooled liquid, it is known that there is dynamic heterogeneity, which increases as we go to lower and lower temperature. Certain part of the liquid moves faster versus certain other part of the liquid moves much more slowly. And this concept of connecting the dynamic heterogeneity to the local environment of the system comes from the idea of solids where defects gives rise to dislocation. So now here the idea is that is there something local property of the particle that which gives rise to some kind of a heterogeneity in the dynamics is a question which is asked in this community. And one of the pioneering work here is by Peter Harwell, who showed that the vibrational modes are like that. The frequencies of the vibrational modes of particles which move faster are softer. So they are low frequency vibrational modes. Now, in the recent time, using machine learning, there has been a lot of study to try to connect the dynamic heterogeneity to the local property of the system. What has been done is basically there are some vectors chosen around a particle or around each particle, and the machine is trained in terms of mobile and less mobile and more mobile. And the machine gives back some information and can predict the mobility and the structural heterogeneity, and the local properties of the system. And there is the property that they describe is basically a softness parameter, which is a weighted function of the GR. Now, I can see that you can't see my cursor, but that's okay. So now local property of the GR, it's basically a weighted GR, and this weight is what is the machine gives us back. Now the question is, so now this same thing, the softness parameter was used by Professor Andrea Liu and others to show that two systems having very similar structure, the radial distribution function is very similar, whereas the dynamics, the second plot here, the dynamics is quite different for these two systems. And what they found is that actually the systems having very similar structure has very different softness. And if you can use the softness parameter to describe the dynamics, then they kind of overlap. That means what they were trying to say is that if I know the softness, I can actually predict the dynamics of the system. Now, as I told you, that these are given by machine, it's machine learning. And as any machine learning problem, we do not know what is the origin of W. We know that it predicts some kind of a modulation in terms of the radial distribution function of the system, but there is no direct connection to the structure. Now that is where we started working on the problem. We had earlier developed a molecular mean field theory. In the mean field theory, we had described the dynamics of a system in terms of a mean field, which kind of tells you that each particle is caged by the surrounding neighbors, and the cage is described with the structure factor of the liquid. And in terms of the structure factor, we could describe, and we used the Ramakrishna-Yusuf free energy functional to describe this mean field. And we got a potential. So basically, we said there's a caging potential of each particles, and the caging potential is described with the structure. Now we thought, okay, why don't we use the softness of this caging potential and see if it can predict the dynamics of the system. So we found the softness of this caging potential for a large variety of systems, plotted the softness versus the dynamics, and we found that yes, for the WC and LJ system, it does appear to overlap, but when I go to larger variety of system, here I also have active systems, so basically out of equilibrium systems, and also systems of different density, then we find that they do not really overlap. Now, what is happening here? If I look at the relaxation time, the temperature dependence of the relaxation time, we see there is a large variation. Now, for all the systems, I can write the relaxation time in terms of an Arrhenius expression, but let's remind you that because these are not all Arrhenius, so the delta E here is temperature dependent. So basically, I'm trying to write it in terms of this Arrhenius expression, but the delta E is temperature dependent. And now when I do this and plot the delta E of these systems, again, which is obtained from the relaxation time, and plotted against the softness parameter, I see that for all the systems, it shows a linear behavior, which means that I can write the delta E in terms of the softness parameter with a system dependent, the C prime and B prime are system dependent parameters, which tells me that the temperature dependence of the activation energy is described by the temperature dependence of the softness parameter. Now, if I use this and write the relaxation time in terms of delta E and write delta E in terms of softness, then I can actually describe the dynamics in terms of the softness parameter. And for a large variety of systems, we see that the softness parameter shows can predict the dynamics with a system dependent. So there is a master plot, but there is a system dependent C prime and B prime parameter. And this is what we had done for, now note here, this was done for the average properties of the system. And now our aim is to see if we can use this to describe the origin of dynamic heterogeneity, which means we are now trying to study the local properties of the liquid using the same theoretical formulation. Now, there is local fluctuation in dynamics, and that is exactly what I told you. And in an amorphous system, there is local fluctuation of structure. And it is well known that correlation between average quantities does not guarantee a correlation at the microscopic level. So our aim now is, does this correlation between the structure and dynamics that I showed you in the previous slide, does it still hold at a microscopic level? Now, to understand that, we had to rework the theory to study the local property of every system, because structure factor cannot be obtained locally, but the radial distribution can be found. Now, the details are given here. Once we do that, we find that indeed we found that there is a variation in the softness parameter at a particle level, and there is a probability distribution, and this probability distribution has a temperature dependence. The particles becomes harder and harder as we go to lower and lower temperature. Most interestingly, we find that there is a lifetime of the softness, and this lifetime of the softness of each particle has a strong correlation with the dynamical, the lifetime of the dynamics. So basically, they decay at the same time scale, which means the softness are long-lived. What we also found is that as we go to lower temperature, the softness determines the dynamics, the time scale of the dynamics quite well. Whereas at higher temperature, this dependence is not so, means there is not much difference between the softness, like the dynamics of particles with different softness values. Now, what we did now is we tried to now look at the local dynamics mobility of each particle and connect it to the local softness. And the pink is a plot at a higher temperature. At higher temperature, it appears that when I plot this log of PR, which is basically the fraction of particles which are mobile with a certain value of softness, we see that there is not much of temperature dependence. Not much of softness dependence. They behave in a very similar way. But as I go to lower and lower temperature, like the black plot here, we see that particles with higher softness values has a chance probability of movement is much high. Now, if I plot this log, so basically what I'm trying to say is lower temperature, because the cages are long-lived, there is a higher correlation between the mobility and the local property, like the softness of the particles. Now, if I plotted the log of PR versus 1 by T, I can see that they show an Arrhenius behavior with an energy, activation energy, and all these plots, they cross at a particular temperature, which is basically the onset temperature of the glassy dynamics. Now, what does this mean is this theory is valid only below the onset temperature, and above the onset temperature, the prediction is not correct, which makes sense because I can only define a cage below the onset temperature and not above the onset temperature of the glassy dynamics. Now, what I have shown you here is that there is a structural heterogeneity, and this heterogeneity, actually what I did not get a chance to show is it becomes broader as we go to, like it increases, the heterogeneity increases as we go to lower temperature, and these structural heterogeneities are long-lived at lower temperature, and I could also connect the mobility with the structural heterogeneity. So essentially what I could show here is that the structural heterogeneity is what drives the dynamical heterogeneity of the system, and most of our studies are similar to the predictions that is given in the machine learning studies. And with that, I would like to thank you for your attention.
Thank you, Sharika, for this very insightful talk. Shishar is now open for question. Yeah, Shrikant, you may go ahead.
So, Sharika, one question that people ask about the machine learning defined is what exactly is it capturing? And it's not very, the answer is not very clear. So, in your case, can you say something that's more?
Yes. Yeah, exactly. So that's what we were trying to understand, what machine learning is capturing. And my cursor is not working here, but if you can see that the potential is written in terms of the direct correlation function and the radial distribution function. So basically what we are seeing is kind of interaction potential. So direct correlation function is kind of an interaction potential between two particles at a two-body level, and the GR gives you the probability. So it's basically the interaction potential the particle feels, but since this is a theoretical formulation that we have done at two-body level, then it's a two-body interaction potential. Effective interaction potential. So this is clearly, the theory has a very nice insight of what this is. And we cannot directly connect the WR to this function because we work with this potential, and the inverse of that is related to the softness, whereas the machine learning directly relates the softness, takes a product of WR and GR connected. So I couldn't directly connect the WR to any functional form, but I know what we do is basically we calculate the inverse of the depth of the potential, which is basically the softness.
Okay.
Does it answer your question?
Partly, but that's fine. I think I'll talk to you more.
And we do see even we see facilitation. You know, the propagation of softness is also seen here very nicely.
Okay, that sounds interesting. Thanks.
Yeah, I think we might take another very quick question. Edwin, would you like to ask a quick question? Otherwise, you can post in the chat box and Sharika can answer. Yeah.
Yes, ma'am. I just want to quickly ask, has the softness parameter been linked to the viscosity? I mean, what would one expect if one studies the variation of the viscosity as well as its relation to the softness parameter?
So the local viscosity is what you're trying to tell.
Yes.
That. So we haven't calculated the local viscosity, but we have calculated the local vibrability parameter, and it does correlate directly with the softness. We do plan to connect it to the elasticity. Basically look at the G infinity behavior and try to see if there's a correlation between softness and the G infinity also, and along with that the elasticity. So these are the things which are, now we are going to try to connect the softness with other properties and see which correlates and which does not. And Shrikant, this is what we see, a propagation of softness even when the particle does not move. So this is kind of a facilitation, and this is very similar to what the machine learning has shown.
Thanks.
Okay, thank you, Sharika. Let's move on to the next talk. So our next speaker is Vinay Vaiva. Vinay is a graduate student at the Institute of Mathematical Sciences in India. Vinay works on rheology of complex fluids and glassy system. Vinay is going to talk about rheology of glassy binary mixture. Vinay, over to you. Could you share your screen?
Yeah, is this visible?
Yes, yeah, please go ahead.
Yeah. So hello everyone. So I will at first thank the organizers for giving me this opportunity to present our work here. So today I'm going to talk about glassy binary mixture, a mixture where size ratio is a bit large between the particles. And in particular, I will talk some interdiffusive properties of such mixture and also some rheology of such mixture. So this work has been done with my PhD advisor Pinaki Chaudhary and our collaborator Jürgen Horpak at University of Düsseldorf. And if you want to see this work in detail, please refer this to archived versions. Okay, so in our daily life, we see a variety of materials where having various applications in industry and in our also daily life, where particles size ranges from a very small value to very large value. The microscopic understanding of dynamics and rheology is very important to develop various new applications and also designing many new materials. So a couple of works have happened in this direction to understand such mixtures. One of the early work is some experimental work is by Imhoff and Daunt, where they use hard spheres to construct a phase diagram. What do they do? So this on this axis, this is a packing fraction of bigger particles, and this is the packing fraction of smaller particle. And they show that when there is a small packing fraction of smaller particles with the bigger particles, so there exists a fluid phase of smaller particles with the crystalline phase of bigger particles. But if you increase the packing fraction of smaller particles, you start seeing a fluid phase of smaller particles with the glassy phase of bigger particles. But if you further increase the packing fraction of smaller particles, you see the coexistence of glassy phase of both the species. So our regime of interest is this, where fluid phase of a smaller particle exists with the glassy phase of bigger particles. And a couple of works have happened recently also. This is one of the work where people have tried to understand microscopic structural changes happening in such systems when smaller particles are introduced in a system of bigger particles. So they see that initially when a small number of smaller particles are introduced, the system shows softening, and when a large number of smaller particles are introduced, then the system starts becoming hardened again. So in particular, I would like to mention these two works, which are very much related to our motivation that we have actually tried to understand the rheology of such mixtures. Is actually, if you see the time scales between the two species, you will notice that there's a huge separation between the time scale of bigger species and the smaller species. As can be seen here in the diffusivity of bigger species and the smaller species in such system. The diffusivity of bigger species with the increase of density of the system decreases very rapidly and almost vanishes at some point, which can be estimated using the mode coupling predictions. But the smaller particle diffusivity, even at very high density, is finite. So the physical picture is something like this. So you have a frozen matrix of consisting of bigger particles, and in that frozen slowly moving matrix, you have small particles which are moving. So this is the physical picture. And if you talk about rheology, then we know as of now, there are only few works which have been done in order to understand the rheology of such mixtures. The interesting thing here is the time scale competition. As I mentioned on the previous slide, huge time scale separation between the relaxation dynamics of the bigger and the smaller species, and the time scale which is introduced via the shear actually competes with the time scales of the bigger and the smaller species. In a way, we see some complicated interplay between these three time scales, and that I'll be talking in detail in coming slides. So our goal here is to understand the microscopic, to develop actually the microscopic understanding of such systems, of the microscopic observations that we do when the system. So just briefly, I'll discuss about the model that we have used. So this is the same model which has been used by these guys, Bachmann and Horbach, in an earlier paper, which I mentioned on previous slides. So here there is a soft interaction between the particles, and this is a 50-50 mixture. Bigger A particles are shown in green here, as you can see. Smaller B particles are shown with dotted blue, actually small dots. And the average size ratio between bigger and smaller particle is close to 2.85. And as you can see here, most of the space occupied by the species is by the bigger particles. And there is a slight polydispersity that we have taken just to avoid the complications into the mixture to have between the bigger particles, and the smaller particle diameters are fixed. And there is a very weak coupling between the bigger and smaller particle. Temperature of the system is kept fixed. And at high densities, we have used hybrid swap Monte Carlo and molecular dynamics algorithms to equilibrate the system. And in general, when we get the configuration, we do molecular dynamics simulation by varying the density of the system to a very small value to very large value. So at first, we focus on the interdiffusive to understand the interdiffusive property of such system in the context of such mixtures where the size ratio is a bit large. So interdiffusion is related with the intermixing of the two species present in the system. In order to measure this, what one can do, one can track the center of mass of motion of any one of the species. For example, bigger species will be considered. Then we can measure the center mass of the bigger species, and using this center mass motion, we can calculate the mean square displacement of the center of mass. And using that, we have expression of DAB, which is the interdiffusion coefficient, can be estimated. And if you put different parameters here, then in a way you can relate also this interdiffusion coefficient with the center mass diffusivity of the system. Okay. So we have done the measurement of mean square displacement of the center mass of the A species just to estimate the interdiffusivity of the system. And then we have a single particle mean square displacement of the bigger system and a bigger species and a smaller species. So from here we can estimate DACM, and from here we can estimate DA, and from here we can estimate DB. All of these have been plotted as a function of density of the system. And in particular, I would like to say about the bigger particles. You can see this shows some power law decay with the increase in density at relatively smaller densities, which can be fitted with the mode coupling predictions. But when we go to higher densities, solder-like exponential decay like we have here appears. And surprisingly, this diffusion coefficient of bigger species at these densities coincide with the diffusion coefficients measure of the system center mass of the system. So in a way, bigger particles diffusivity is following the center mass diffusivity of the system, and also the interdiffusion of the system DAB is following the smaller particle diffusivity of the system. So we can see here that at very high densities even there is a finite diffusivity of bigger species, and which is following the center mass of the system, which is presenting some unphysical picture because we expect a frozen type of situation at very high densities from the bigger particles because they are forming the glass. So just to rectify this, what we suggest that these measurements, single particle measurements of bigger particles mean square displacement and smaller particle mean square displacement should be done in their respective center mass. And if we do so, then this dotted line that you are seeing here are the measurements in their respective center mass. And we see here that there is a prolonged plateau which appears, and also this solder goes away because you cannot estimate diffusivity here, and even here there is some diffusion also starts appearing. So all of this happens if we do the measurements of these single particle quantities in their respective center mass. Now, just keeping this rectification in mind, I would like to shift the focus on the rheology part, where we actually shear the system along the x direction at different shear rates. and we see that the system shows initially yielding, then after it goes to some steady state, and we do the measurements in the steady state at different shear rates. So again, I would like to remind you, when we shear the system, in a way we are, in some way we are introducing a time scale to the system, and this time scale has to compete with the two widely separated time scales present in the system between the bigger and smaller species. So here are the control parameter is the shear rate that we apply, and also the density of the system that we vary, actually from a very small value to a very large value. Now, at first, I would like to report some macro measurements. So this is the steady state stress measurement as a function of shear rate, and we see that initially there is a linear behavior between the stress as a function of shear rate, which is a Newtonian behavior. And as we go to slightly higher density, we start seeing some curvature appearing into the system measurements, and this is a signature of non-Newtonian behavior. And if we go to further at high densities, we see that these curves even don't bend, and it seems like that at vanishing shear rates, they will be showing some finite value, which is an emergence of some finite yield stress at vanishing shear rates. And if we see the viscosity of the system, then at a small densities, we see there is a regime of Newtonian viscosity, and at high density, if we go to, then we see there is a decrease in the viscosity, which is actually shear thinning of the system. Now, the high density measurements that we have, where we see the emergence of yield stress, we take this data and we do Herschel-Buckley fit to estimate the vanishing stress at vanishing shear rate, sigma naught, and we can estimate this, and this shows a very nice fitting, and we can plot this estimated value as a function of density, partial density of the system of a species, and this is the behavior. Now, if we see the micro picture, so something interesting appears here. So here what we do the mean square displacement measurement of bigger species, mean square displacement measurement of a smaller species, and these measurements are done at different shear rates, and also in the absence of shear, these dotted measurements are there. So we see at very small density, where both bigger and smaller particles are fast, when we apply the shear, almost both the species don't respond to the shear. I mean, the measurements in the presence of shear and in the absence of shear are roughly same. But if we go to slightly higher density, which is close to the mode coupling density of the system, mode coupling density of the A species of the system, then here we see that A particles are responding to the shear because they have sufficiently slowed down, and these smaller particles are still not responding because they are fast. But if we go to a very, very high density, we see that both the particles are responding to the shear. This is because of the time scale matching between the shear and the intrinsic relaxation of the bigger and the smaller species, because at very, very high density, smaller particles also become slow. So we see a density dependent response from the bigger and smaller particles in the system. So if we put all these micro and macro measurements together, which was the goal of this study, then here in the macro part, we plot stress as a function of shear rate, viscosity as a function of shear rate, and on the other side we have.
Vinay, sorry to interrupt you. You have 2 minutes left.
Yeah. I have. This is the one more slide. Yeah. Okay. Diffusivity of bigger particles as a function of shear rate, and diffusivity of a smaller particle as a function of shear rate. So this is the micro measurements as a function of at different densities. So we see that at very small densities, there is a Newtonian behavior here. And in this part, we see that diffusivity is not being affected of bigger and smaller particles by the shear. At intermediate densities, we see that non-Newtonian regime is there, and the diffusivity of only bigger particles start actually showing some variation. And at very high density, we see that both the diffusivity, bigger particle and smaller particle, where are actually responding to the shear. And also at these high densities, there is a this diffusivity of bigger particles can be estimated some power law, but this diffusivity are showing some finite vanishing value at vanishing shear rates, finite value at vanishing shear rates. Now, just to understand the role of smaller particles, what we do, we consider different composition of the mixture, like 100-0, where we have only bigger particle, no smaller particle, 75-25, and 50-50, all the previous studies that I reported. So here we see that at any given density, when we increase the number of smaller particles, system actually becomes fast. And if we see the measurements in the presence of shear, then the viscosity of the system decreases, which is the softening of the system, which has been reported by some earlier studies also. So just to conclude, we have taken a binary mixture where the size ratio is a bit large. We actually done some interdiffusive measurements to conclude that measurements should be done in their respective center mass. That's all we have done. Then we reported all the previous measurements in the context of rheology. And another important point that I would like to highlight is that the system shows emergence of rigidity of the at a density which is close to the mode coupling density of the bigger species, and also that at this stage bigger particles are almost frozen, but even system is showing rigidity, but smaller particles are moving sufficiently fast into that system. So just with these all details, I would like to conclude, and I would like to just remind that if you want to see in detail, please refer these two papers on archive. Thank you.
Thank you, Vinay, for this very interesting talk. Session is now open for questions. Okay, so if you have some question, please post it in the chat box, and there will be also breakout room for discussion. And so I think Vinay would be happy to answer your question, whatever query you are having.
Yeah,
so let's thank Vinay once again, and move on to the our next lecture. It will be a 25 plus 5, 30 minutes duration talk. We have the invited speaker, Professor Shrikant Shastri. Shrikant is a professor in Theoretical Sciences Division at Jawaharlal Nehru Center for Advanced Scientific Research in India. He works on statistical mechanics of a wide range of liquids and soft matter systems, colloids, gel, granular material, dynamic of glassy behavior, and many other systems. So today, Professor Shastri is going to talk about yielding in amorphous solids under cyclic shear. Shrikant, over to you.
Okay, so thank you, Rumi. I'm having some trouble with the presentation, so I'm going to just try to work with the full screen mode.
Okay, yeah, and, you may try.
Let's see if that is good enough.
And also maybe our technical team might help you also in case.
Yeah, but is this going to be okay? If you can.
Yeah, yes, it is fine. It is visible very much.
Okay, good. Yeah, because if I do full screen, I can't see anything except the presentation. So this is better for me. Okay. Okay. So let me begin by thanking the organizers of this wonderful series of meetings that I've been attending over the years. Yeah, it's been nice to have it in person, but an online meeting is the next best thing. So thank you for the invitation. I'm going to tell you about work that we've been doing over some time now, trying to understand yielding in amorphous solids. And the new thing that I hope to spend some time on today is looking at how that happens when the applied deformation, which is cyclic in the cases that I'm going to be talking about, is also asymmetric, and I'll describe to you what that means exactly. This is work that is done in collaboration with several people. Himanshu Bhaumik was a postdoc at JNC, Manoj Adhikari, a PhD student, and Giuseppe Fofi at Orsay, Mohitin Mungan, Jack Parley, and Peter Solich. So some of this work has been published in the articles that I list here. I can, well, okay. So here is a brief outline of what I'm going to tell you about. I'll just sort of very quickly introduce mechanical behavior of amorphous solids. What are the kind of things that one worries about? I'll then tell you about simulations of glasses under symmetric cyclic shear, and highlighting some of the important messages that come out of that. And then I'll spend some time describing attempts to model this behavior in several ways. And Among the particular features that I'm going to then talk about is something called fatigue failure. I'll say what that means when I get to that. And then I want to spend some time talking about the phenomenology that emerges when one applies deformation in an asymmetric fashion. There are some interesting new observations there. Okay, hold on. Okay, so mechanical behavior, in particular yielding and mechanical failure of solids are of obvious importance. I show, you don't see my cursor, do you? You do see. There's a time lag.
Yes, yeah, we could see your cursor.
Right. So there are some examples of things that fail and yield. This includes hard or molecular glasses, such as glass, so silica glass, metallic glasses, but also various soft solids that are shown at the bottom. And so now, as compared to crystalline solids, yielding and amorphous solids display distinct characteristics, and these are investigated in diverse settings. This corresponds to the diversity of amorphous solids from molecular glasses to soft matter, including sort of geophysical scales. Now, even if one considers glasses made of a given substance, something that's important to note is that glasses are not unique. Properties of glasses vary significantly depending on how they're made, in particular the degree of annealing or what people also refer to as glass stability. And this degree of annealing or glass stability has implications for mechanical behavior as well, and mechanical failure of glasses. And this is something that has been explored considerably in recent times, both for deformation of glasses uniformly, as well as using cyclic shear protocols, which have in particular also been investigated in computer simulations. And so the graphic at the bottom of the screen basically shows that there's a wide range of both scales of the component particles as well as type of glasses that one is interested in principle in explaining the yielding behavior and rheology of. Okay, so in this talk, I'll talk about yielding behavior under cyclic deformation only. And it turns out that when one subjects an amorphous solid to cyclic deformation, the behavior in certain senses is richer. It needs more sort of precise modeling in order to comprehend the behavior. And as I already mentioned, I will talk about both symmetric and asymmetric shear deformation cases. There are interesting differences and new insights that arise. Okay, so here is a quick summary of the simulations. We perform simulations of several model glasses. I will mention them when I show the results, but I'm not going to spend any time describing the details. The only thing I'll mention is that a couple of the models for which I'll show the results are binary mixtures of Lennard-Jones particles, but we also have results for silica, which I'll show. In computer simulations, when one talks about glasses, these are basically local energy minima that are obtained by considering liquid configurations equilibrated at a given temperature and subjecting them to local energy minimization. And the different temperatures at which you simulate the liquid correspond to different degrees of annealing of the glasses. And we study yielding behavior under what is called athermal quasistatic shear. The athermal basically means that there is no temperature in the problem. You're applying deformation in such a manner that you're always sitting in a local energy minimum. Quasi-static refers to the fact that you deform very slowly or infinitely slowly, which also therefore removes any role of inertia from the problem. And shear, just to define, is a volume preserving deformation, which can either be applied by hand, as we do normally in simulations, or by using periodic boundary conditions, or you can affect this by the application of stress. And when I talk about cyclic shear, basically one is going to be applying strain back and forth in the manner that is shown in the movie that's running, and shear deformation leads to both elastic response, which is sort of the default thing one would think of for small deformations, but also plastic rearrangements. These are shown in the cartoon that's running at the middle of the slide on the right side. Basically, what you'll notice in that is that as the deformation is increased, at some point a finite subset of particles rearranges in a manner that doesn't correspond to the globally applied strain. These are plastic deformations. And we study the properties typically of configurations at the end of each cycle. That's mostly the results that I'll be showing, but we also sometimes look at what happens through the entire cycle. Okay, so let me first tell you about symmetric cyclic shear. The state of glasses when subjected to cyclic shear evolves with the number of cycles, and this exhibits considerable plasticity for depending on the case, and therefore and also correspondingly annealing. Annealing, so simple-mindedly, means you're accessing lower and lower energy states. Now, when the deformation amplitude is small, the energy of the system per particle depends both on the amplitude of strain applied. This is shown on the leftmost panel, as well as the initial state or the initial energy of the glass that one is deforming. And you see this again in that leftmost panel, where the blue or the same colored curves, which correspond to the same strain amplitude, do not reach the same energy at the end of a given number of cycles. On the other hand, if the strain amplitude is large enough, then the final energies reached depend on the strain amplitude, but they no longer depend on the initial conditions. And this is shown in the middle, or the second from the left panel, where the energies you see of curves that are starting at high energy as well as low energy of the same color, which corresponds to a given strain amplitude, are reaching a common energy. And the difference between these two sets is before, in the first set, the energies that are finally reached become lower and lower as the strain amplitude is increased, whereas in the second set, the energies actually go up as the strain amplitude is increased. So there is some change of behavior, and this also corresponds to an apparent divergence of timescales to reach the steady state. And this is shown in the third panel from the left. If one looks closely at what is happening in the second set of strain amplitudes, what one finds is that particles become diffusive. That is, if I look at configurations at the end of each cycle, they do not come back to the same place, which they do when you're in the small amplitude regime, but they diffuse. Okay, so there is a what's called an absorbing to a diffusive transition that is taking place. And also, if now in the steady state one looks at the energies through the cycle, and this is shown in the top right figure. If you follow the blue arrow, this corresponds to increasing strain amplitude below this transition point. And what one finds is that in the steady state, you basically describe like a single parabola with larger and larger amplitude as you go to larger strain amplitudes, whereas when you undergo this transition, this parabola splits up into a butterfly pattern so that the minimum energy is no longer at zero strain, but at some finite value. So in other words, the stress-free configurations in the second regime correspond to finite strain, and this finite strain I will be referring to as plastic strain, and it's going to be important for the story. So the behavior that I described is roughly what one observes if one starts with relatively high energy classes, and that's seen at the top of the left curve. So with increasing strain amplitude, the energies are decreasing till you hit some transition point, which we identify with yielding, above which the energies of the glasses begin to increase. Okay, but there is a dramatic change in behavior if one goes to glasses which are better and better annealed below some threshold value. And in this second regime, the well-annealed regime, glasses do not, these are energies at the end of each cycle, as I said, stroboscopic energies. They do not show any change with increasing strain amplitude till they suddenly make a jump to the yielded branch. Okay, so there's a change from what appears to be a continuous yielding transition to a discontinuous yielding transition as a function of annealing. And this is also reflected in the manner in which the stresses vary as a function of the strain amplitude. The stresses that I'm showing are the maximum stresses that are experienced, which correspond to the maximum strain amplitude that I apply. Okay, now this behavior is what I show here is for one particular model glass, which is called the Cobb-Anderson binary mixture. But this is the same kind of behavior is also seen for other glass formers, other glasses rather, silica glass, and also two-dimensional glass, which is a binary mixture glass. Therefore, the behavior seems to be fairly generic. Okay, so the question is, how can we think about this and explain it? And one of the main ways in which people have been trying to model yielding behavior and sort of elastoplastic response of amorphous solids is through what are called elastoplastic models. And what you do in these is to imagine dividing the system that you have into small blocks or mesoscale blocks that are shown in the illustration on the right-hand side. And then you try to define rules for how each of these blocks may reorganize when it undergoes the plastic rearrangement, and then when one such event happens, you ask how does it affect the other blocks in the system, and there is an understanding that whenever there is a local rearrangement, a local plastic rearrangement, this leads to propagation of stresses in the rest of the system, and this sort of comes from a continuum elastic description of the material. But the important thing is when there is such a propagation of stresses, you can trigger plastic rearrangements elsewhere in the system. Okay, so there are these two components. The second is sort of this long-range linear elastic propagation of stresses, which are well understood at a certain level. But then you have to have a clear idea of how you describe the behavior of each of these local blocks, or rather, each of these blocks and rules for plasticity in these blocks, in order to get a correct description of the mechanical behavior of these solids. And till recently, one thing that hasn't been built into these models is the idea that the local states of each of these blocks can be diverse, that there are different degrees of annealing and therefore stability of these of glasses which have to be taken into account. So what I'll describe now is a recent attempt to build a minimal model for how plasticity arises, and the key ingredient the key ingredients of this are one, which I've already mentioned, which is that there is a distribution of energy levels that you can have. And the second thing that's very important is that the strain at which any one of these sort of locally stable structures can have a minimum energy, which I call the reference strain or the plastic strain, can be different. And this is fundamental to describing plasticity. And the third ingredient simply is that for a given locally stable state, there is a range of strain amplitudes under which it behaves elastically, and at the end of which it yields locally, right? And so since I'm talking about athermal shear, now I have to define a transition rule that says I can make a transition to any one of these other states, which I call mesostates, as long as the energy at the strain at which the transition takes place of the other state is lower. Okay, so with these, so this is a minimal description of what an amorphous solid is like. And so with this description in mind, the first thing I do is to look at what the behavior is that emerges if I just imagine that I'm performing this dynamics for a single block. Okay, and interestingly, even the behavior at the level of a single block captures a lot of the key features of the simulation results. So this is now the result that is shown on the left top graph of running this mesostate model for a certain number of cycles. Okay, starting with initial states which have different energies. And what one finds with, I won't repeat everything because I have to keep an eye on time. I find the same kind of pattern that I saw in simulations. Okay, and in trying to understand how this behavior arises, in particular, the fact that there is this apparent threshold energy, which was not there in the original description of the model, what I do is to look at the distribution of energies that I find myself in at the end of a given cycle as a function of the initial energy of my system. And this is therefore a bivariate distribution, which I show in a color map here for different strain amplitudes. Okay, so this is a particular case which is sort of cleaner to describe. What one finds to a first approximation is that the final energy that I reach at the end of a cycle does not very much depend on what the initial energy was. Okay, this is a bit of a surprise, but it's a feature of the model. And therefore, what I have to ask myself is, what is the probability that at the end of this cycle, I reach a final state which is stable under subsequent cycles of shear, and that energy below which I'm stable for any given strain amplitude is shown by this horizontal line. And what you see is that as the strain amplitude increases, the possibility that I remain or that I reach an energy that is stable under subsequent cycles becomes smaller and smaller. And therefore, at some point, I do not find myself in a stable state. And so you can imagine or you can think of this as sort of a random walk that I perform on the energy axis, where at the end of each cycle, I find myself in a different energy. And if that energy goes beyond a certain threshold, I get trapped. And that's the dynamics of the system. And this can be sort of mapped into an even simpler model, which is basically a random walk in a potential with an absorbing boundary. And without sort of going into all the details of the model, I just show and the results. I show here the result of the calculation for this model, which is basically qualitatively very similar to what I found in the earlier cases. And in particular, I have an expression for the yielding amplitude, but interestingly, but not surprisingly, this yield amplitude actually depends on how many cycles of shear that I apply, and therefore it's not a very uniquely defined quantity. Basically, if I perform sufficient number of cycles, I always do get trapped. So if the but the dependence on the number of cycles is extremely slow. Okay, so this is a good description of what the model does. But one can ask, is it a good description of an amorphous solid where, in fact, there will be a well-defined yielding amplitude? And in order to sort of look at that situation, what one considers is to add to this description the possibility that when I go beyond this boundary into the absorbing part of the energy axis, I continue to have a finite probability for escaping. And you can imagine this finite probability of escape as arising from some form of activation. It could be thermal activation, or it could be an activation that arises from mechanical noise, which I'll say more about in a minute. And when one includes this possibility of activated escape, two things come out. One is that there is now a well-defined yielding amplitude, which is fixed by the rate of escape of stable states. And secondly, I have the possibility of shearing the system at amplitudes that are above, and then the probability of yielding increases, or rather the time scale for yielding decreases as my amplitude increases more and more above this threshold. And this is sort of an approach to understanding fatigue failure, which I mentioned before, which is basically the observation that if I perform cyclic loading, there is a typical number of cycles before I fail, and this number becomes higher and higher as I decrease the strain amplitude till I reach a point where it appears to diverge. Okay, and this is called the fatigue limit, and this is something that material scientists worry about. So we have a way of trying to get at this fatigue limit. So the next thing
Because sorry to interrupt you. You have 5 more minutes.
Okay, I'll get to the rest in 5 minutes. So the next thing we do is to take this basic description and perform a mean field calculation through a Fokker-Planck description. And the key difference from what I just mentioned earlier, where I introduce some kind of an activated escape by hand, is that in this description, the noise that enters the consideration is something that arises from the activity that is going on in the system. So in a mean field description, you're sort of still describing the state of in your thinking one local region of your glass or amorphous solid, but what happens there is subject to mechanical noise that depends on whether there is plastic activity elsewhere in the system. And this mean field theory also captures the yielding diagram that I've been showing in different avatars. But more interestingly, what emerges is that if one looks at, I'm sorry, this slide always takes time to load. I don't quite understand why. If one looks at how much plastic activity there is, one finds that this activity exhibits in a certain range of strain amplitudes non-monotonic behavior. So if I'm at sufficiently small amplitude, the activity sort of decreases and goes to zero at a finite number of cycles. And this is an amplitude that's below the yield point. But if I go above, I find that the closer I am to this yield point, the longer it takes for me to reverse the trend of decreasing activity and then yield. And this is very reminiscent of fatigue failure. This behavior can be associated with a time scale. And if you look at that time scale, you have an initial exponential, but eventually power law divergence of this time scale as you approach this yield point, which we now associate with what materials scientists call the fatigue limit. And so this is very, it's an interesting development. We have some kind of a theoretical description of this phenomenon. We still don't have a very good microscopic picture of what's going on. But let me take 2-3 minutes to talk about asymmetric shear. So this is basically shearing the solid to one side. And you might ask, does it really make any difference? Isn't it just a matter of shifting your reference strain value? But the interesting thing is that shifting of the reference strain value is something that's not only notional, but it has to happen physically. Okay. So if we take the simple case of a poorly annealed glass, in fact, what one finds, this is shown most clearly in this energy versus strain diagram. The minimum of the energy initially is at zero strain, but if I keep cycling to one side, that minimum shifts to a finite strain value, and this finite strain value shifts higher and higher as I increase the amplitude of the strain, roughly at half of the amplitude that I'm applying, and then the system yields. So this seems like, okay, I just shifted everything by half the strain amplitude that I'm applying asymmetrically, and then I can think of it as basically being the same phenomenon as the symmetric shear case. But something very dramatic happens when I consider well-annealed glasses, right? So what happens here is basically nothing till I reach a finite strain value, which it turns out corresponds to the yielding strain amplitude for the symmetric case, and only then one sees considerable plastic activity. And so here is the energy versus strain amplitude diagram that you should compare with what I showed earlier for the symmetric case. Basically, for well-annealed glasses, there is no change till I reach the yield strain of the symmetric problem. And then one has a regime where the energy goes up. But if you look at sort of the state of the final, the system reaches in the steady state, it is non-diffusive. Therefore, you're still below the yielding point. Okay. And to get some insight into what is happening, one can look at the strain value at which the energy is minimum. And as I told you, for the poorly annealed glasses, this basically very quickly goes over to half the amplitude of the asymmetric strain. But for well-annealed glasses, it basically remains at zero till you cross the yield strain of the symmetric case, and then it begins to shift towards this eventual line of half the asymmetric strain amplitude. And okay, there's sort of very interesting things that happen in the course of this unusual behavior, which I will skip. but one can ask whether this can be described using the model that I talked about earlier. And it turns out that with certain modifications, the model that I described to you earlier captures the behavior that is seen in the asymmetric shear case. Now, the last thing.
Shrikant, if you could wrap it up. I mean, time is up, but you can wrap it up quickly. Yeah, that would be great.
This is the last slide. So, which is to look at system size effects. Basically, for the poorly annealed glasses, you don't see much system size dependence beyond a certain small size limit. But for the well annealed glasses, the yielding transition gets sharper and sharper and moves towards the yield strain amplitude of the symmetric case. And this has a very unusual consequence, which is when you perform asymmetric shear, yielding happens for well annealed glasses well before it happens for poorly annealed glasses. Okay, this is the opposite of the trend that you see for symmetric shear, and this therefore reveals a lot of very interesting properties that one must keep in mind and understand, or rather, and account for when one is describing plasticity in amorphous solids. So here is a summary. Thank you for your attention.
Thank you, Shrikant, for very insightful talk. We can take one couple question. I mean, a quick question. Yeah. If someone has a quick question, please go ahead.
Andrea.
Yeah, Andrea. Yeah, please go ahead.
Hi.
Hi, Andrea.
That was really interesting. So just want to understand this asymmetric case. So I'm trying to think of how to put my question because I'm a little confused about it. So you're saying that the difference is that for the really well annealed glasses, the differences for the well annealed glasses, not for the poorly annealed glasses, are the same. I guess that's the main thing, right?
Right.
And for the well annealed glasses, it's because they're so well annealed at the state of zero that doing it asymmetrically really makes a big difference.
Yeah. So basically,
state.
For poorly annealed glasses, there's always plasticity before yielding, and therefore the system evolves towards a state where it centers its plastic strain halfway through the strain amplitude that you're applying, whereas well annealed glasses do not have plasticity before yielding in the symmetric case, and so only when you go beyond do you see any plasticity, but it still doesn't correspond to yielding behavior as defined by there being diffusive motion from cycle to cycle. So there is intermediate range of plasticity which does shrink with system size. We're not very clear yet whether it completely vanishes. But the main point is what happens at smaller strain amplitudes is very different for the well annealed case. So, but the interesting consequence of this is when you apply asymmetric shear, a well annealed glass will yield before a poorly annealed glass does, which is, yeah.
Very cool. Yeah. Thank you.
Yeah. So thank you, Shrikant, and let's move on to the next talk. We have an eminent speaker, Professor Bulbul Chakraborty. Bulbul is currently the Init and Net Ansel Professor of Physics at Brandeis University in USA. She works on systems far from equilibrium. Her group explores complex behaviors in a wide variety of systems, particularly granular and glassy materials, and also collective behavior of active systems. So today Bulbul is going to talk about the collective behavior of particles with noisy interaction. Bulbul, over to you.
Can you see my screen?
Yes. Yes.
Okay.
Could you
So let me begin by thanking the organizers, and I wish I could be there. I haven't been in Kolkata for 2 years now. This is the longest that I've ever stayed away. So I'm going to talk about something that is maybe slightly unusual in this context, but for this session, I'm still going to talk about disordered systems, but disordered systems made out of particles that are different from normal atomic, molecular, or even colloidal systems. So I've listed my collaborators on this slide. This has been a long-going effort, but the people that are highlighted are in dark letters here are the ones that have contributed to the work that I'm going to talk about today. So let me begin by just setting up the problem. So this background that you see are the kinds of particles that I'm interested in constructing a statistical mechanics framework for. So you see a scale bar at the bottom. So that's a millimeter scale bar. So these particles are big. They are all different. They have surfaces that can interact with that touch each other. When the particles touch each other, the surface roughness comes into play. They are all different shapes. So there is very little possibility that we can sort of write down an interaction energy or an interaction potential for these systems and proceed with StatMech the way we usually do. Moreover, these are big enough that thermal motion doesn't play a role at all. So these are these are completely non-Brownian. There's no Brownian motion happening. So the question is, how do we try to understand the collective behavior of these kinds of particles? So the type of materials, as I just said, are there's friction, adhesion, all kinds of surface properties that enter these interactions. So this is what I mean by noisy interactions, in the sense that there's noise at the point of two particles contacting. So even if it's in principle possible to maybe determine interactions, in practice it's not feasible. But often these systems are instantaneously in a state of force and torque balance. They're in mechanical equilibrium. They're not in thermal equilibrium, but they're in mechanical equilibrium. So these are the kinds of states that I'm going to be focusing on. And the kinds of questions we ask are, can we generalize concepts that come from equilibrium statistical mechanics to these kinds of systems and construct statistical field theories that might be able to capture the collective behavior of these systems. So I'm going to begin with a striking example of why I think this approach, that this is not pie in the sky, this is actually, there is a possibility. There are indications that we can extend concepts from equilibrium statistical mechanics to these completely non-thermal, completely out of equilibrium systems that might help us understand their collective behavior. So the example that I'm going to show you is not the main focus of this talk. This is just for motivation. So this is a phenomena called discontinuous shear thickening. And the background here is cornstarch suspensions. So these are experiments done in Heinrich Jaeger's group and show stress measurement, so rheological measurement, stress as a function of strain rate. You just heard Srikant talk about rheology, so you are familiar with it now. So what you see, these are the suspensions, so particles suspended in a normal Newtonian fluid. And what you see is at low packing fractions, low densities, you see Newtonian behavior, but there is this abrupt change in the stress as a function of strain rate as you increase the density. So this phenomena is known as discontinuous shear thickening. And if you increase the stress even more, the system actually jams. So this is called shear jamming. If you look at the viscosity as a function of the stress, the imposed stress, then you do see, so Newtonian would be the viscosity doesn't depend on the stress at all. Here you see this sort of rapid change in the viscosity. So that's the phenomena. So now what we recently observed by this work is done in collaboration with Itai Cohen's group and Cornell, is if you take these kinds of viscosity versus stress data, and this one is actually for cornstarch, you can collapse all of the data using something that's very familiar in equilibrium statistical mechanics, which is known as crossover scaling. So I'm not going to get into the details, but what I'm showing you is this beautiful data collapse over orders of magnitudes of the viscosity, over many, many packing fractions, over all of the stresses, and for two different suspensions, a silica suspension and a cornstarch suspension, and they both obey the same scaling function. So that to me is a remarkable indication that maybe, you know, there are underlying field theories that are not so different from, they're different, but they're not so different in their concepts from equilibrium statistical mechanics. So from this kind of scaling collapse, we can actually construct an empirical renormalization group flow and reconstruct the phase diagrams that we get from using these scaling functions. So this is pretty remarkable to me. So for this system, we are now at the state that I would say, you know, we were decades ago when we knew in equilibrium systems about scaling from Widom and Kadanoff. We still don't have theories for that. But it's an indication that I think that the quest for statistical field theories for these kinds of systems, the quest for ensembles is not so misplaced. So now I'm going to switch to the actual focus of this talk, which is on a simpler system or a simpler question, and that is stress transmission in granular medium. So what I'm showing here on top on the left is experiments from Bob Berenger's group from 2 decades ago. And what you're seeing here is a vertical pile of grains made out of photoelastic material. That's how you can visualize the force change. But the message from that I want you to take from here are two from the top figure, that these exist as solids only because of gravity. So granular materials, because they have purely repulsive contact interactions, do not form a solid unless there is some external stress on it. That could be pressure, could be shear, could be just gravitational forces. And the second feature, of course, is what is known as these force chains. So this is the figure A that you see on the left is the granular pile, and B is now the response to a tiny point force that's put on top. And the bottom two figures, C and D, show just the response, so subtract off the background. So you see this tenuous chain of particles or contacts that bear the forces. So this is what's known as the force chains. The other message that I want you to take from this slide is that ensemble average quantities actually mean something. So what you see at the bottom are the ensemble average responses of 3 different kinds of packings with 3 different underlying contact geometries. And so these ensemble average quantities are robust, or one could say the distributions are robust. So what you'll see from the theory that I present today is that there is an analogy between these force chains and a kind of charge propagation in a generalized electromagnetism framework, which has vector charges instead of the normal scalar charges that we have in ENM. But it's still a U1 gauge theory, but with different kinds of charges and different kinds of quote unquote electric and magnetic fields. And what the other thing that I'll show is this granular media, which have these different kinds of ensemble average properties due to different underlying contact networks, are actually behaving like a dielectric in this ENM. So it's a polarizable medium, and their polarizability is different depending on contact networks. So with that, let me just set up the theoretical structure. So we are going to rely heavily on the fact that these networks that are created by external stresses actually satisfy a bunch of constraints. So we should think of this as a constraint satisfaction problem. So there's a global stress tensor, which is either coming from external forces, gravity or pressure and shear that's imposed externally. And every grain, every particle satisfies the constraints of force and torque balance. So this is satisfied locally. These are local constraints. Then there is a friction law on each contact. There is positivity of forces, which are inequality constraints that need to be incorporated or at least kept in mind. So with these constraints, these are still highly degenerate systems. What do I mean by that? That for a given set of global forces, global stresses, there are many configurations that satisfy all these constraints. So how do we construct a field theory that imposes these kinetic constraints and predicts the stress state of these systems? So that's the field theory that we are looking for. Now, there is precedence for this, even though it wasn't very familiar to this community. There are well-defined, there's been a long history of using, of constructing field theories and looking at phase transitions in systems that satisfy constraints. So I'm going to start with the sort of the epitome of a frustrated system. So where this kind of theory has been mostly studied is in spin liquids, both classical and quantum. Here I'm just going to show you a classical spin liquid, which is the ensemble of ground states of the triangularizing antiferromagnet. So in the triangularizing antiferromagnet, I have the frustration is encoded in that I cannot satisfy the antiferromagnetic requirement on every bond on a triangle. So then the best I can do is have triangles which have only one bad bond. So in this triangle that I'm showing you here, there is one pair of spins that are aligned in the same direction. So that's the bad bond. The other two are good. So this is a constraint saying every triangle can have only one bad bond. That can be translated into a picture on a dual lattice, the honeycomb lattice, where for every bad bond that is intersected by the bond in this honeycomb lattice, I draw two arrows pointing up, and for every bond that's satisfied, for every bond that is satisfied, I draw the two bonds going up. For every that's unsatisfied, I draw single arrows going out. So this is just a mapping of my physical system, but this mapping is mathematically extremely useful. It tells me that I can think of this as lattice versions of fluxes of an E field or a B field, whichever way you want to think about it, and that flux is conserved. So two arrows come in and two arrows go out. So with this is now a well-established theoretical framework. You can construct a continuum field theory by relying on the fact that this flux conservation gives me a Gauss's law, the Gauss's law of divergence E equal to 0, or I could think of this as divergence B equal to 0 and write B as curl of some vector potential. The statistical field theory that emerges then is just like ENM, but there is a coupling constant, a stiffness constant. So the message is that local constraints like this are known to give rise to emergent gauge symmetry at low energies. And what I mean by that is I'm focusing only on the configurations here that do not violate the constraint. Any spin flip in my original Ising antiferromagnet that violates these constraints are much higher energy than all of the systems that are encompassed here. So this is an emergent theory at low energies, and I'm looking at only low energy excitations. The crucial things that come from here is that in these spin liquids, the spin-spin correlations decay algebraically. because these are sort of Coulomb phases, they look like ENM, but this is not a broken symmetry system. So there are gapless collective excitations that are not spin waves. There is no long range order. There is no broken symmetry. All of these features, the power law correlations, the existence of gapless modes are a consequence of gauge invariance, not broken symmetry. So the question that we asked a few years ago is there a similar emergent theory at the heart of the elasticity or the stress response of jammed solids whose solidity emerges from the applied stress itself? And the answer is yes, otherwise I wouldn't have been here talking to you. So, sorry about that. So let me set up the problem for you. So as I said, I have to think about the jammed solids as created by external stresses. That could be as simple as external pressure. So what I'm showing you here is these dark blue arrows are the external forces that are exerted on a system. I have this system of grains. I've just given you a 2D example here. So the grains are the disks that you see. Now there is contact interaction. So at every contact, there is a force and a contact vector joining the center of the grain to that contact point. So this R and the F. And at every contact from this R and F, I can also define a stress tensor that I'll come to in a minute. So what are the local constraints? So similar to this constraint that we saw in the dimer model or the triangular lattice Ising antiferromagnet, where the fluxes have to add up to 0. Here, the forces on every grain have to add up to 0. That's my first equation up here. And the torques on every grain have to add up to 0. That's my second equation. So those are the constraints. And what I'm interested in constructing a field theory for is the analog of the E field in the previous, the toy problem. And what that is a force moment tensor, which is just the outer product of this R and F that lives on every contact. So from that, I can construct a coarse grain stress tensor just by summing over them and averaging them. So we are interested in constructing a field theory, a continuum theory of the stress field. Beginning with, so the contrast with crystalline elasticity is here. I don't want to rely on the concept of a broken symmetry and a well-defined reference structure and a displacement from that. I want to rely on the constraints of local force and torque balance to construct a field theory. So the properties of this coarse grain stress tensor, so when I go to the continuum, is that the force balance constraint translates into just the divergence of the stress tensor being 0. If I now actually had a force of gravity, let's say on every grain, then it wouldn't be 0, it would be equal to the component of that force in the I direction. And the torques add up to 0. This is a subtlety that I don't have time to go into here, but in frictionless systems, the torque density is identically 0. But for frictional systems, there is a torque. There is a finite torque density. But because of the fact that on every grain, the torques have to add up to 0, then this torque density can only live at the boundary of my. So in my box that you're seeing here, the red dotted line is if I did the calculation, I would see that the torque density, as I keep coarse graining out, lives only on that boundary. So the bulk stress tensor is symmetric, and the anti-symmetric part of it is only a boundary contribution. But so this is a subtlety of the problem. So what do I do with this? So the point is, with this picture in mind, I can map this system onto what is known as a vector charge theory, vector charge U1 gauge theory. So this has been, again, it was developed for us, so we didn't have to do too much work. So the way to think about it is this my jam solid is like a polarizable medium in a kind of electromagnetism where the charges are vectors. The charges are not scalars. And the Gauss's law is a Gauss's law for a symmetric tensor, a symmetric E field, and gives me these vector charges, right? So divergence of the E field is now a vector because E is a symmetric tensor. So the mapping is that the charges in the vector charge theory, the free charges map to the external or body forces that I impose, like gravity, in my jam solid. The bound charges of my polarizable dielectric medium become the contact forces. So this is the mapping. I'm giving it to you in a very pictorial way. But with that, we know how to then construct our field theory. That's because this vector charge U1 gauge theory was developed for us. There's a whole set of Maxwell's equations. It looks exactly analogous to usual ENM, but of course, all of its properties are very different because the charges are vectors. And one crucial property is that in addition to charge conservation, which we know of in just in usual ENM, here the charge angular momentum is also conserved. And what that means is that maps onto, as you'll see in a second, is just the force and torque balance constraints. But also, because of this charge and charge angular momentum conservation, if I think in terms of this theory as an ENM, a vector charge, let's say if the charge is pointing in vertically downwards, it can only propagate along its own direction. So this is really the source of these force chain-like structures that we see. So to understand the jam solids, we needed to take this vector charge theory and just generalize it to a dielectric. So we do the usual thing. There are now bound charges, and there's a dipole which comes from the dipole moment. There is an electric displacement field, which I have denoted as a D here, because now I have a polarizable medium. So this is all standard, except everything is generalized to tensors and vector charges. So if I have a linear dielectric, then the D tensor is related to the electric field tensor just through a polarizability tensor, which now here is a fourth rank tensor instead of just a second rank tensor as in usual ENM. And so I'm looking at only electrostatics of this dielectric. So the electrostatics, the second equation here that you see on the right-hand side, which says the double curl of the E field is 0, then gives me a solution as the electrostatic potential is the solution to that equation. And the electrostatic potential here is now a vector. So the E field is written as the last equation here. Sorry, I can't find my cursor, so I can't point. So if you see this, then this looks the construction that we have in this vector charge theory looks exactly like what elasticity theory would look like, but with a big difference. So in normal elasticity theory, I have the divergence of the stress tensor is equal to the external force, and then I have a strain tensor, and the stress tensor is related to the strain tensor through the elastic moduli. So in this formulation that I have just presented to you, there is really no concept of displacement fields or strains, but there is an E tensor that looks very much like a strain tensor, and the polarizability of the medium is emerging as the elastic moduli. So the crucial difference, and this is why this difference emerges, because I have no unique reference structure in these jammed solids. The crucial difference is that I now have a gauge potential, the electrostatic potential, playing the role of a displacement field, and I have a field that looks like the strain tensor, but it's not constructed out of displacement fields. And the elastic moduli are not material properties. They emerge from the kinds of contact networks that are actually created by the external stresses. So they show up as coupling constants in a field theory and can be determined by measuring stress-stress correlations, stress response, all of that. So I'm going to just end by quickly showing you a couple of results from the theory.
Sorry to interrupt you. You have 5 more minutes.
Yeah, so I'm just going to, thank you, Rumi. Thank you, Rumi, yeah. So I'm just going to show you some comparisons of both experiments and numerical data to theoretical predictions. So I'm beginning with the comparison of stress-stress correlations measured in experiments compared to the theory. So on the left, what you see are from the experiments, the top panel, the top row, shows on the left-hand side grains colored by how large their XX component of the stress tensor is. And if you look at that, you see that these are now sort of lining up in the X direction. In Q space, in Fourier transform space, the stress-stress correlations are shown in panel B. So these are experimental measurements. On the right, 2 columns of the top figure, the red dots are the experimental measurements and the black curves are the theoretical predictions. Now, the theoretical predictions are fitted to the experiments for just one elastic modulus tensor. So sort of the overall strength of the correlations is all that we fit to. That's the only thing. And with that, you can see that the theory provides a remarkable description of what's observed in these systems. And the chains that you see of the X component in the second row, it's the same configuration, but now the grains are colored by Y, stress component, and they go in the Y direction. So force chains are really nothing different from saying that the stress-stress correlations are very different along the longitudinal and transverse directions. And that comes just from the Gauss's law condition. So quickly showing you that. So in real space, the stress-stress correlations, let's say if I'm looking at the X component, would be they're all power law, but they're positive along the X direction, but die off quickly and become negative in the Y direction. So the theory provides a remarkable description of a whole range of experiments and numerical simulations. We have no way of predicting the elastic modulus tensor yet. So that's why we don't have that microscopic theory, but the elastic modulus tensor actually encompasses all of these other constraints that I was talking to you about. So I'm just going to quickly show you. So this is a measurement of a response to a point force, and on the left-hand side, you see numerical simulations, and on the right-hand side, you see the theory. So let me just, because I'm running out of time, I'll end there, but there are other numerous examples of where we have seen this remarkable agreement of numerics and experiments with theory. So let me stop presenting and take questions if there are any.
Thank you, Bulbul, for this wonderful talk. Yeah, so session is now open for questions. Srikant, please go ahead.
Hi, Bulbul, I have 2 quick questions. One is, you know, in about this crossover scaling, I also talked a little bit with Jim about this recently. I'm trying to understand how much is it actually telling us, because it says you have scaling functions which are different in different regimes, and a crossover scaling describes like the totality of what you're seeing. So, but
telling you that the discontinuous shear thickening is just a consequence of crossover scaling. There's nothing happening at that line. The only critical points are along the shear jamming line. It's remarkable to me that crossover scaling works here, because it's saying that friction can be thought of as a relevant perturbation to the frictionless jamming point, and that's all I know at this point. I don't have a theory for it. It's just remarkable that and the same scaling function works for multiple different suspensions.
Okay.
So scaling works is all I'm saying. I'm not saying anything more than that.
Okay. No, that part is clear, but I was trying to see what can I get out of it in terms of.
It says that you take different systems, you're controlling them through stress and packing fraction, but only a particular combination matters.
Well, there's more than
Sigma and phi are not the whatever combination gives you in some way in the Wyatt-Cates series the number of frictional contacts. It could be something slightly different, but it's some relevant parameter that's saying that it's taking you away from the frictionless jamming point.
Okay, I'll wait for my second question. Andrea has her hand raised.
Yeah, I think Andrea. Yeah, Andrea, please go ahead.
Yeah. So okay. So there's a place where the strain tensor breaks down, right? And that's when you have plasticity, when you have rearrangements.
No, it breaks down from the get-go. I don't have any stress-free reference configuration.
Yeah, I understand. But you have this field theory instead.
Oh, you're saying where does plasticity enter this theory?
Exactly. Can you look at nonlinear excitations that take you from one allowed state to another?
Yeah. So that comes in through, just like in crystalline elasticity, you have singularities in your strain tensor. Here they'll show up in singularities in my stress tensor, which is a violation of that double curl constraint, right? So I have singular stress fields. But in this theory, interestingly, if I stick to the structure of the theory, as soon as I have a violation of that double curl constraint, I have to have flow, which to me is really interesting because I cannot get it without a B field. So it's saying as soon as I have singularities in my stress tensor in this, it's not going to yield, but it's going to have some kind of flow because it will immediately generate a B field, which to me is really interesting. So this is something that I'm trying to really understand now. And, I want to talk with Srikant and everyone else too, because the one thing that we don't know is I know what sources the B field, but I don't know what the B field is. The source for the B field is actually the momentum tensor. So the divergence of the B tensor is the momentum density. So I cannot have a B field without flow, all right? Or the B field can be created either through the curl of E or through a source. So I'm saying if I have a curl of a stress tensor that's not vanishing, it'll create a B field. I can't have a static kind of disclination density here, seems to me.
So it should be related somehow to strain rate.
Yes. So this is something, or actually what this tells you is what's the dynamics of the analog of the strain tensor.
Yeah.
Yeah.
Exactly.
Yeah.
I
Nice.
think, thank you, Bulbul. I think we have to
you,
move on
everyone.
to we have to move on to the next talk. Whatever question we have, there will be a breakout room after Andrea's talk. So please wait for further discussion. And so let's move on to the next talk. So this is the final talk of this session. we have a distinguished speaker, Professor Andrea Liu. Andrea is currently the Hepburn Professor of Physics at University of Pennsylvania in USA. She's working on soft and living matter system, studying emerging collective phenomena of active systems, problem of jamming, and glassy system. Today, Andrea is going to talk about how glassy systems relax and go with the flow. Andrea, over to you.
Oh, this is terrible. I need to, okay, hold on. I need to give Google Chrome permission.
For Chrome permission?
I need to give Chrome permission to share my screen. I have to go into system preferences. Sorry about that. I should have checked that before. Okay. Yes. Okay. All right. I think I'm okay now. There's some. It's because of recording permission. So let me see if I can do this now.
Yeah. So you have to present your.
I can't share my screen. I go to system preferences because of screen recording permission. I am sorry about this. Camera. Yes. Recording permission. I'm not sure where I'm supposed to give recording permission.
Is it a Mac?
Yeah, it's a Mac. I'm not used to using Google Meet. I'm sorry. Maybe if you could just not record it, is that possible? Or is it, or is that not the issue? Screen recording. Okay.
Yeah, PK, I think, yeah, organizers would be able to tell PK Anando if you could.
Hold on. I think it could just be a problem for sharing it anyway. It may not have. Okay, there. Okay. I'm sorry. Now I have to quit Google Chrome and re-enter it. I'm so sorry. Okay.
Yeah, sorry for this interruption. I think Andrea is using first time as he told that. So please, yeah, wait for a few minutes. She will log in.
Okay, I'm back.
Okay, great.
Yeah. Should be able to share now. Yes. Okay, now let me just start my talk.
Yes, yes. Yeah.
Okay, great. Sorry.
Yeah, we could see. Yeah, great.
Okay.
Yeah.
I thank you for all of you who are staying this late and been so patient with this. So I'm going to just dive right in. I'm going to talk about how we're using machine learning to actually try to build a theory. And so, right, let me just start out by reminding you, we're all statistical physicists, right? And our mission in life is to understand collective behavior and, to gain a microscopic understanding of collective behavior. And to do that, right, we've been using statistical physics. It's been really successful, and it does several things for us. It does a huge dimensional reduction problem by taking all that microstate information and reducing it just to distributions of a few relevant variables. And those relevant variables, those microscopic variables, are what provide that bridge from the microscopic to the macroscopic scale. But there are some problems, right, where statistical physics has had a hard time. And the glass problem is sort of exhibit A that people always mention when it comes to that, and that's what I'll be talking about today. So when a liquid is cooled through the glass transition, right, the point is that the particles don't order, they don't crystallize. You cool quickly enough so that they don't have time to crystallize. And the relaxation time, the time it takes for the system to equilibrate, rises continuously and extremely rapidly as you lower the temperature. And when the system can no longer equilibrate on a reasonable timescale, that's when we call it a glass. So, as I said, statistical physics does these two things, dimensional reduction and providing this bridge. And machine learning, right, has been designed by computer scientists precisely for dimensional reduction. And so that raises the question, right, can we use machine learning to help us do statistical physics? But, right, we're still left with this question, which is really a physics question, which is what is the relevant microscopic variable that we want to look at to get help with to get help from machine learning to identify in order to understand, in this case, glassy dynamics. So to do that, we really want, I would argue, is a structural order parameter for glassy dynamics. So, right, what do we mean by that? Well, in an ordinary liquid, any particle can rearrange, right? But in solids, that's not true. In crystalline solids, we know that it's only particles at dislocations that are far more likely to rearrange either due to thermal fluctuations or due to some mechanical load. That's where plasticity and flow occur, is at these defects. So, you know, it's been a question for more than half a century for glasses and glassy liquids. Can we identify sort of comparable defects, or alternatively, some sort of structural order parameter that can predict the probability that a particle will rearrange, or that is correlated with the probability that a particle will rearrange. And that's been, you know, that's been the big challenge. And the thing that we've been working on for several years is to use machine learning to do that. It turns out it's incredibly easy to do it with machine learning. So what do we do? So the idea is the following. It's based on the pair correlation function, the way we do it. So we define a parameter, which we call the softness, which is a particle-based variable. Okay, so that's my microscopic variable. And it is a weighted average of the pair correlation function. When I have non-spherically symmetric potentials, it's actually important to include a higher order term here, a three-body term. But for the spherically symmetric systems that I'm talking about today, you can think of it just as a weighted integral of the local pair correlation function. So this is the local pair correlation function that tells me, you know, where the particles are around particle I. Okay, it's not the average. So, and the weights here have been chosen by machine learning, okay, to have a very strong correlation so that the softness has a very strong correlation with the probability to rearrange. Okay. And so if I look at the average pair correlation, not the local one, I have peaks and valleys. It turns out that the weights here are strongest at the peaks and valleys, okay, of the average pair correlation function. In other words, it's the particles with higher softness, particles that are more likely to rearrange, have lower first peaks and higher valleys. Okay, actually lower peaks in general and higher valleys. All right, so that's what softness is. Let me just show you. It has a distribution that's quite close to Gaussian. It's a little bit skewed, okay? And this is what it looks like as a function of temperature. At high temperatures, it's the red curve, and as I move to lower temperatures, the whole distribution of softness just shifts downwards, okay? So it becomes less soft. Softness has spatial correlations on the scale of about a particle, okay? So all the results I'm going to show you today are for the 3D Kobe-Anderson model, which is a binary mixture of Lennard-Jones particle, non-additive Lennard-Jones particles. All right, so what we're going to do is we're going to obtain the weights at a single temperature, okay? And then we use that to calculate the softness fields for the systems at different temperatures. Okay. And here's the remarkable thing that makes softness such a useful quantity. If I plot the probability that a particle of softness S will rearrange, okay, so each softness here is a different color. So high softness particles here are red, okay? If I plot the probability that particles of this high softness will rearrange, what I see is that it is a straight line when I plot the log of the probability versus 1 over temperature. That's an Arrhenius plot. And what that says is that the probability is exponential in 1 over the temperature, okay, with something that I can interpret as an energy barrier. And that depends on softness. So the slope here tells me the energy barrier. That energy barrier decreases as I go to higher softnesses. Can you guys see my cursor? I don't know if you can, probably not. So as you, on the plot on the right, oh, you can see my cursor, great.
Yes.
Okay, so yes, as I go to higher softness, you see the energy barrier is lower, okay? Corresponding to higher probability to rearrange. And lower softnesses, that's the blue, have higher energy barriers, okay? So softness, by just measuring the structural quantity, okay, just measuring the local pair correlation function and weighting it accordingly, I can pull out the characteristic energy barrier that is required for that particle to rearrange. That's a huge simplification, because the energy landscape, remember, is a 3-dimensional landscape in a system of n particles. Okay, and it has of order e to the order n minima, a huge number of local minima in it. And but we can, and pulling out the energy barriers, you know, by the nudged elastic band or something like that is incredibly hard and time consuming. You can only do it for very small systems. But here we can get information about systems that are as large as we like, okay, by just measuring their local structure. So I'm going to take this as given. I'm going to take this behavior of the probability of rearranging, and I'm going to say we know these energy barriers and these entropy barriers. All right. Now, I just want to say that this is very general. Okay. This, I just showed you the Kobe-Anderson model. Here's a model for silica, which is a strong glass former, network forming glass, very different sort of glass. But if I look at the probability of rearranging, what I see is that it's again Arrhenius, okay, for particles of a given softness. And this is really nice work, which we're just writing up now by Indrajit Ta, where he's looked at a system of harmonic repulsive shears at different packing fractions. By doing that, you can actually vary the fragility of the system. So you can go, from a strong glass former where the relaxation time is nearly Arrhenius to a fragile glass former where it's strongly super Arrhenius. So very different kinds of glasses. And it holds, he can train a single set of weights across the whole range and look at the behavior. And you can see that the energy barriers depend much more strongly on softness in more fragile systems. He's also done really nice work on the Vertex model, which is a model that actually shows a relaxation time that grows more slowly than Arrhenius behavior, which is sort of unusual. And again, you see that for that behavior, if you look at particles of given softness, the probability of rearranging is still Arrhenius. And the same is true in aluminum polycrystals. So softness, what I'm saying is that softness really tells us the energy barriers to rearrangement across the whole spectrum of behaviors of glasses, and even all the way to ordered systems, okay? So it really is getting at, it really is serving as a structural order parameter across all of these different systems. So now we've got the structural order parameter. What's the point? It's not just to predict that we can get the structural order parameter, right? What we want to do is to understand phenomena. And so what are the phenomena that we want to understand? So this is what's called what we want to understand is dynamics. So this is what's called the overlap parameter. So it tells you how far each the particles have moved from their initial positions as a function of time. So first they have not moved at all. So they are all overlapping with their original configuration. Okay, but over time they move away. Okay, and they're on average you can see what fraction of them have moved away from their original position, and this overlap parameter decays with time. Now, if you look at what happens as a function of temperature, right? As you lower the temperature, going from red to blue here across this thing, as you lower the temperature, you see that it takes longer and longer for the particles to move away, and this decays more and more slowly, right? There's a time scale here. You can also look at the variance from configuration to configuration. Different configurations will decay at different times, and that variance is highest sort of rather close to the inflection point. And so the variance is what's plotted here. That's called chi4. And that variance increases as you lower the temperature. Okay, so you have a peak here that increases as you lower the temperature. And you can pull out two things from this peak. First of all, you can pull out the time corresponding to that peak. That's the relaxation time at that temperature. So time it takes the system to equilibrate at that temperature. You can also look at the magnitude of that peak, and that tells you, how heterogeneous, because this is measuring the variance of the overlap parameter, this measures how heterogeneous the dynamics are. Okay, and they become more and more heterogeneous as you lower the temperature. It's rather like traffic near jamming, if you're well below jamming, then everybody's going at about the same speed. But as you get closer and closer to jamming, you're stuck while everybody else is moving, while other people are moving, right? That's what this is measuring. So the other thing we would like to look at is aging. So what happens when you start at a high temperature where you have the liquid, and now you quench to something that's below the glass transition? What you can see is what happens as a function of time. And here softness is plotted on a black to red scale, where red is high softness and black is low softness. And what you can see is that the system, the distribution of softness is moving down, okay, as you wait, as you watch the system evolve, so that it's getting less and less soft over time. But the probability of rearranging at 3 different ages is the same as a function of softness. And what that tells you is that all you need to know in order to understand aging is the softness. That aging is a structural phenomenon, and the relation of the structure to the dynamics doesn't depend on age. Okay, so these are the kinds of curves that we'd like to understand. These are the phenomena and the behaviors that we'd like to understand. So in aging, what you see is that the relaxation time increases as you wait. The longer you wait, the less soft the system gets, okay? And the longer it takes for the system to relax. So that's what's plotted here. That's just showing this upward trend with waiting time. And similarly, the average softness decays, goes down, right? That's that shift from red to black. It decreases as you wait. If you eventually equilibrate, it will approach a fixed value, right? And it will stop. And that's because the system was able to equilibrate. But if you quench below the glass transition, it'll just keep going down. So, all right. So now let me just stop a little bit, right? And ask again, right? What's the point of this machine learning prediction? So the point, right, as I said, was to understand glassy dynamics. In particular, we want to understand these quantities, the dynamic heterogeneity, chi4. There's a length scale associated with how heterogeneous it is. That's called C4. We'd like to understand the dependence of the relaxation time on temperature, and on if we quench below the glass transition, how does the relaxation time depend on waiting time, the time following the quench. So one approach has been to use machine learning to directly predict future dynamics. Okay, that has not been our strategy. What we do is we're using machine learning to predict which particles, what is the probability that a particle will rearrange very soon, okay? And why do we do that? Well, the idea is because behavior at a future time, right, there's so much noise that it's very hard to predict, and structure actually doesn't tell you very much about behavior at a future time. So what we want, as I said, and what we have gotten is the structural order parameter. And the idea is now what we're going to do is develop a theory, a coarse-grained theory based on this structural order parameter in order to predict statistical quantities at a later time. In other words, we're going to do statistical physics with it. Okay. So just to put this a little bit in context, there are a bunch of different kinds of models and approaches that have been used to describe the glass transition. A bunch is really a vast understatement. Lots and lots of theories of the glass transition. But let me just talk about two classes of them. They're kinetically constrained models that have been successful in capturing a lot of the dynamical quantities that I'm interested in. And these look at the link between structure and dynamics, right? On the other hand, there are energy-based approaches. They use the energy landscape. And that's, for example, the mean field theory approaches that maybe it was too early, but I know Giorgio Parisi talked earlier, maybe he spoke about that. Those capture the link between the energy landscape and dynamics. What softness does, because softness tells us about the energy barrier to rearrangement, it provides a possible way to reconcile these and to develop models that connect structure to the landscape, or at least the energy barrier to the dynamics, okay? And so if we want to build a theory based on softness, we need to look at the interplay of softness with rearrangements. And the point is that soft particles are far more likely to rearrange than the others, okay? But on the other hand, if you have a rearrangement, you change the local pair correlation function around a particle, so you change its softness. And that is what's called facilitation. But the point is that the changes in softness due to the rearrangements have to be consistent because we are in equilibrium, or at least local equilibrium, with detailed balance, okay, and time reversal symmetry. So in the interest of time, I'm going to skip the stuff on that. We have a simpler model, a trap model, where we leave out correlations. And it works on some things, not so well on others. But I'm going to skip straight to what I call the thermal step model for structural elastoplastic model. We first developed these models for plasticity, a zero temperature. And now this is the model for where we only have temperature and we don't have mechanical load or don't have stress and strain. Okay, but we've developed that theory as well. So the idea is we know we implemented on a lattice, so each site has a softness, right? Each site can rearrange with a probability given the energy barriers that we know. If you have a rearrangement, it changes the softness not only of the site that rearranges, but the nearby sites, okay? That has to be consistent with time reversal symmetry. And I'm just going to remind you that the distribution of softness is nearly Gaussian. And it turns out, is what we find from the simulations is that the distribution of the changes of softness is also Gaussian, okay? And there's something that likes to restore the softness, bring the softness towards some value, A, okay? These are matrices because I have non-local effects. And the interesting thing about this is that time reversal symmetry imposes constraints, basically, that this coupling, H, a matrix, depends on the variance of the softness distribution and the change of softness distribution. I cannot adjust those independently. We see that that variance decays exponentially with distance. Okay, so that's facilitation is exponential in distance. And when we implemented this in the model, we get quite reasonable results. So here are the MD simulations in black. Our model predictions are in blue. We can predict how the average softness evolves as we lower the temperature. Okay, that we're not putting that in. Okay, that comes out of the model. Remember the dynamic heterogeneities, these peaks. We can pull out the peak, the time at which the peak occurs. That's a relaxation time. Okay. Again, the black is the MD, the dash blue is our theory. So we do reasonably well on the relaxation time. The peak position, here we've normalized it to the highest temperature. Again, you know, not bad. And we can predict the length scale, the characteristic dynamical correlation length for the heterogeneities. Again, qualitatively very good. The quantitative thing depends on how you choose your lattice site, which we haven't tried to adjust. And we get aging. So if you look at what happens as a function of time following a quench, so these are different quenches. So this is a quench to a high temperature. Each color here indicates a quench to a lower temperature. These systems all eventually equilibrate, so the softness flattens out. Okay, but if you look at it, what you see is that at these times here, they all collapse onto this common curve. Okay, and that is bizarre. Okay, why is that bizarre? Because what happened? I skipped something.
Yeah, and here you have 5 more minutes left.
Okay, I have 5 minutes.
Okay. Including questions, yeah.
Okay. Oh, including questions. Okay. So let me just say that this collapse is weird. It's saying that as you go to lower and lower temperatures, facilitation is more and more efficient at changing the softness with as a function of time, because at lower temperatures, there are fewer rearrangements. So the fact that these are collapsing means that the rearrangements are more and more efficient. They're more, and that is actually captured to a reasonable extent in our model. So just to sum up, we use machine learning to get the structural order parameter, and then and facilitation, the idea that when this particle rearranges, it changes the probability for other particles nearby to rearrange, just emerges from this. We get again, what emerges are the spatial correlations, and we can apply this approach not only to softness, but to any order parameter that can tell us something about the energy barrier. So just want to sum up and thank the people who did the work first on glassy dynamics, and then highlighting especially Sean and Energy, and then the people who worked on these structural elastoplastic models, Gajang and Sean. Thank you.
Thank you, Andrea, for this very insightful talk. Session is now open for questions. So I could see already raised hand. So first, Sharika. Sharika, please go ahead.
Hi, Andrea.
Hi, Sharika.
Yes, I wish I was talking after you. I did not have to give any introduction to my talk then. So I just wanted to ask you, you showed this length scale from the softness length scale, xi to be 1.4. And
Oh, the correlation like for softness, yes.
Yes, and later on you show a length scale that changes with temperature. What I thought was that at that, your previous slide showed that they were almost overlapping, all the temperature.
Yes, so the softness correlation length, so the scale on which softness is correlated is quite short. It's of order of particle. It does increase slightly as you lower the temperature. Okay, we have not incorporated that yet into our theory. So in our theory, that length scale is actually fixed.
So
okay,
the
so that's
plot
things.
here.
So, but what I'm showing here, what?
The plot here on this slide shows it's increasing, right? But your previous slide shows.
This is a different length scale. This is the length scale for dynamic heterogeneity. So this is a dynamical length scale, not the structural length scale. So the structural length scale increases extremely slowly, as you would expect for the structural length scale. Okay. In fact, it increases even more slowly than the point to set length, as far as we can tell. But the dynamical length scale increases much more rapidly.
Okay.
And that is what we capture with this.
Okay, yeah. I guess there are other questions and I can talk to you.
Yeah, I think, it will be good because there are also other people that use. So Srikant, please go ahead.
So, okay, so I want to repeat the question I was asking Sharika earlier, which is, I mean, is there, you define this quantity softness through machine learning, but it is a structural quantity, and it would be nice to be able to say something simple about it. And also, how it might correlate with other things people have looked at. One thing that I find very striking is, I'm just like looking at this paper of Andreas Heuer from many, many years ago, where he was looking at the same plot as you had of relaxation timescales versus inverse temperature for different softnesses. His parameter was the metabasin energy, and he also found this very striking dependence which was Arrhenius for a given metabasin energy as a function of temperature, so is there a possibility that one can sort of connect this quantity to something that going forward you can sort of use without using machine learning? Meaning, what can we learn from the machine? We don't build system that we do. And let me just add a second part of it, which is, have you looked at non-spherical particle systems like silica or water, where the structure is actually going to be very different, that correlates with dynamics?
Yeah. So, okay. So the first question, so because softness has its weights concentrated at the peaks and valleys of the average pair correlation function, what is that telling us? We think of softness as basically a way of quantifying the cage. Okay, so physically we think that's what it is. It can probably be correlated with other things, and we use the simplest, dumbest machine learning method. You can use more sophisticated ones. You can do more sophisticated things. We haven't bothered to do that because it does well enough to pull out an energy barrier, to have a characteristic energy barrier. And it would be interesting to connect it with the metabasins. And I think what Sharika is doing is, theoretically is extremely interesting. And, you know, Indrajit is working with her to try to understand the connection. On the second question, yes, we have done silica effect. There. Here are results for silica where the probability for rearranging is again Arrhenius for silica. We've done dimers and trimers. That was with Doug Durian. So we've done particles of different shapes. And we've done oligomers with Rob Riggleman. So you know, so short chain polymers. So yeah, it's not hard to generalize this to particles of other shapes. And the nice thing, right, in the case of the dimers and trimers with Doug, those were experiments, you know, because this just relies on the configuration. As long as you can do particle tracking versus time, you can do this. And so it's very straightforward to apply this to experiments.
Okay.
Yeah.
So I think since it's been quite late, so there are a few more questions I could see. Bulbul has raised hand, and there are also questions in the chat box. So there are breakout rooms been created. So we have a scope to have elaborate discussion. And so before we go to the breakout room, let us all unmute ourselves and thank all the speakers of this session and for the beautiful, it was very wonderful and insightful talks. Let us all give a big round of applause. Yeah, so now I will hand it over to the organizer and they would guide us how we can join breakout room. Yeah, please, over to you, PK or Anando.
Okay, thanks, Rumi, for coordinating things. Okay, so there are breakout rooms, I mean, which are serially given based on your talk number. So you can go there and talk with the